Right, hello everybody. So today we're going to be talking about optimization problems. And so what an optimization problem is you're trying to find the best way to do something. So you're trying to optimize whatever it is that you're doing. So for my engineers, you could be trying to find the best way to do something by minimizing that error. Or if you're a business person, you might want to maximize profit and maybe minimize your costs. So these problems are just taking our calculus, everything we learned from calculus, and putting them into real world situations. And so what I'm going to do before we even start any problems is just to break down how we're going to solve these problems. After this, we'll just do a bunch of examples because honestly, it's the best way to it's the best way to learn these problems. So the first thing that we need to do when we are given an optimization problem is to understand that problem. So our first goal is to understand the problem. And this is true for any word problem, really, is you want to understand what it is that they're asking you to do. The next step is, and you don't have to do this each time, is to draw a picture. Label all your variables. And write down any information given. Now for this part, you don't need to draw a picture each time. If it is helpful for the problem, then go ahead and do so, but it's not something that you will have to do each time. And actually for the first problem, because I'm gonna make the first problem really easy so that we can just get the steps down, we are not gonna need to draw a picture for that one because I just wanna show you guys how to go about an optimization problem. Now the third step is you want to determine which quantity is to be maximized or minimized and for what range of values of the other variables. And that sounds a little bit wordy, but let me write that down and then it'll make more sense when we do an example. So we're going to determine which quantity is to be maximized or which is to be minimized in terms of your variables. And so when you do this and you determine this is what I want to be maximized or which one do I want to be minimized, you most likely will have for a set of range of variables. And this will make more sense when we do an example and you'll see exactly what I mean. And for what range of values of other variables. I guess a really good example of this would be, let's say that this is a really famous optimization problem, and you'll probably see this in your homework. If you're trying to maximize the area of some type of fencing or floor, and you only have such a set of material, only so much material, then that range of values for the other variables is how much material you have in order to optimize your area. So that's kind of what we're doing here. So we have what's called a constraint on material, and we still need to maximize that area. So that's what we're going to be doing. So I guess that's the best way that I can put that. And then we're going to write a formula for the quantity to be maximized or minimized in terms of the variables. And this will most likely involve more than one variable. It doesn't happen all the time, but it happens a lot where it happens to have more than one variable. Okay. So if you have more than one independent variable, we will find additional equations. So if there's more than one independent variable, we'll find additional equations. And we're going to use these new equations to express your formula in terms of only one variable. Okay, perfect. So this seems a little bit weird and wordy, but all that means is if you have an equation for your set of value for the thing that you're trying to maximize, for example, going back to that area problem, we're trying to maximize area. The first thing that comes to mind is maybe if it's a square box or a rectangular box, then my area is going to be length times width. Okay, but if I have a restriction on how much material I can use, right, that has to do with, like, if I'm fencing something, that's going to have to do with how much perimeter I'm allowed to use for my length. So then I have the equation of an area and the equation of a perimeter. And so I'll have two variables like length and width. And I don't really want to differentiate something in terms of two variables because then I'm going to have to do implicit differentiation. And that's not something that, I mean, it's not hard to do, but it just makes it easier if we don't have to do that. So in order to avoid doing that is we can solve for one variable and plug it into the other one that we're trying to maximize in order to differentiate. And this will, like I said, make a lot more sense once I do an example, but I'm just kind of giving you an idea of what that's going to look like. Okay, and so since we're optimizing a problem or optimizing something, right? When we optimize something, we're trying to find the maximum or the minimum. And so if you're thinking maximum or minimum, the first thing that you should come to your mind is everything we did in 4.1 and 4.3. When we were looking for max and mins, we were looking for the derivative and we set it equal to 0 because that's when we got the maximum value of something. Okay, so that's what we're going to be doing. We're going to differentiate this equation with respect to independent variable. Here I didn't want to say to differentiate with respect to x or differentiate with respect to y, because maybe you're not dealing with x and y anymore. If you're dealing with length times width, you might be differentiating L or differentiating W. Or if you're trying to find the error, maybe you're differentiating with a different type of variable. So it doesn't really matter what variable you're differentiating with, as long as it's your independent variable. And we'll do a lot of examples, at least 3 or maybe even 4. And then the next step, the final step, is we're going to optimize using methods in 4.1 and 4.3. Okay, so these are all the tools that we're going to use in order to optimize our problems. And so it's just kind of a breakdown. Like I said, you don't have to write this down each time, but I just wanted to give you guys something to kind of look at the steps, because really optimization is just doing a bunch of problems over and over again until you kind of get the hang of them. And we'll do an example in just 1 second. Okay, so let's do a really quick example. This is a really simple example just so that we can get the process down. So we have a positive number cubed added to another positive number is 256. They want us to find the maximum product of two such numbers. So the first step is to understand the problem. What they want us to do is, given the information given above, find the positive number cubed added to another positive number is 256. They want us to find the maximum product of two such numbers. So the thing we're trying to maximize is the product of two numbers, right? We're trying to maximize the product of the two numbers that also satisfy this top part here. So that's our goal. So what I want to do here is we now want to introduce a couple variables. So a positive number cubed, let's call this positive number that we're going to cube x. And then we're going to add it to another positive number. So since it's a different positive number, let's call this number y. And then the positive number cubed added to the other positive number is 256. So that tells me that that first equation, right, is x cubed plus y, and that equals 256. And I'll actually show you what this means, and you'll actually do this each time for each of these problems. And then the second equation is going to come from the fact that we want to find the maximum product of two such numbers. So we want to find the maximum product of two such numbers. Means that we need to optimize the product of the two numbers. And so we need to come up with a function that we need to optimize. And so that function that we want to optimize, we can just call it f because it's a function. And we're going to say that f equals x times y. And so this is what we're going to call what we want to optimize. And since this equation here needs to satisfy the one up top, we're going to call this our constraint. And so if we look back onto how I kind of broke everything up, here we need to determine what it is that needs to be maximized in terms of the range of variables. So this is basically the range of where our values are coming from. Sometimes it's an equation, sometimes you're just looking at the domain of your function, and that's okay. But the thing is, we have to make sure that both of your equations that are what we're maximizing is still satisfying this one on top. So we need to keep that in mind. So each time that you do an optimization problem, you'll have a constraint and you'll have something that you're optimizing. Okay, so now our goal is we need to optimize this equation here, but the problem is I have an equation of x and y. And I don't really want to do implicit differentiation. And actually, I don't know how that would even help, because when we do implicit differentiation, we end up with a rate. and we don't have a rate, so that's not going to help. So what we want to do is we want to do this fifth step here, which is if we have more than one independent variable, which we do, we have an x and a y, we want to solve for one equation and plug it into the equation we're trying to optimize and then differentiate. So what we're going to do is we're going to use our constraint, and you'll do this each time, and we're going to solve for one variable. Here, the easiest variable to solve for is y, because y is all by itself. It's not cubed, nothing. So we'll solve for y, and then once we solve for y, we'll plug it into our optimization problem. You'll always plug it into your optimization problem because you want to find the maximum of that product. We need to differentiate that equation. So we're going to go ahead and do that. So we're going to use our equation 1 and solve for y. So if I solve for y, move x cubed over to the other side, I get y equals 256 minus x cubed. And now I'm going to plug this into my optimization problem. And so now my optimization equation is just now going to be a function of x, because here our function is a function of both x and y. So here we have f of x comma y, which didn't help. That's why I didn't write that down earlier. But now since we're going to plug that into another equation, we are going to just have one variable. So that's going to be x times 256 minus x cubed. Okay, and now we can distribute that x in, and we'll end up with 256x minus x to the 4th power. And so that's our new function. And now we can actually just optimize this function. And so how do we do that? How did we do it in 4.1? How did we do it in 4.3? We took a derivative and we set it equal to 0. So that's what we're going to do. We're going to take the derivative of f of x. And so the derivative of f of x is 256 minus 4x cubed. And remember, in order to find that maximum number, we need to set it equal to 0. And now what we're going to do is just solve for x. So if we solve for x, we move the 256 over. We're going to get negative 4x cubed is equal to negative 256. And then so we get x cubed is equal to positive 64. We cube root both sides. And then we end up with x equaling 4. Okay, perfect. So now that we end up with our maximum value for x, right, we've found this max value. That's going to be in here. That's going to satisfy that optimization problem. Now, our goal is to find our y value as well. So we need to do that. So in order to find the y value, remember that no matter what, our equation needs to satisfy this equation. And that's how we're going to find the maximum product of those two. So now what we're going to do is we're going to plug x into our constraint and then find that y value, that additional independent variable. So remember that our constraint was x cubed plus y is equal to 256. So we'll write 4 cubed plus y equals 256 and solve for y. You solve for y is going to end up equaling 192. Okay, so this is our other variable. And now we need to report the maximum. So the answer is, right, if we multiply these two together, so if we do x times y, it will be 4 times 192, which is 768. Perfect. So this means that, so here's the answer. We'll write it in words. When you do the other problems, this is not really a big wordy problem. When you do the other problems, I do want you to express it in terms of like what's going on with the problem. So just be aware of that. I'll show you what I mean in just 1 second after we do another example. So we'll say that the numbers are 4 and 192. The product is 768. So that is our answer. Okay, so this is what we did, is we read the problem, we understood it, we identified what our constraint was. This is what I want you to do each time. We identified what we're trying to optimize. So that means we need to identify what we're going to take the derivative of and set it equal to 0 to find the maximum value. And then we solved for one variable in our constraint and plugged it into our optimization problem. And after that, we just solved for our x, or our maximum, our critical number. In this case, we didn't really need to test. We didn't need to test on the number line whether this was a min or a max, just because of the context of this problem. Everything was kind of strictly positive, and we don't really need to deal with that with this type of optimization problem. So I won't need you to do that for this problem. And then after that, once we found our critical number, we know that this was our maximum. And so after that, we are going to, actually what you could have done is you could have tested this if you wanted to, right? So let me rephrase that. You can decide to test them because so once we hit this critical number, you could decide to test your critical number. I didn't, just because of the context of the problem, but it's a good idea and a good habit to do so, because we did that in 4.1 and 4.3. And how sure are we that this is not a maximum? How sure are we that this is a maximum and not a minimum, right? So in order to test it, you can test 4, and then you'll test a number between after 4 and before 4 and after 4 on the derivative. So for example, you could have tested 3 and 5. And if you plug in a number like 3 into this equation here into your derivative, you'll end up with a positive number. So go ahead and try that on your own. And then if you plug in 5 into your derivative, it most surely will be negative. So this tells you that this is definitely a maximum value. So it's a good idea to actually test them, and maybe I should have gone back and tested it, but I knew that it was going to be a maximum. But it is good habit to test them, because what happens if you have more than one critical number that comes out of here? Then now you have to figure out which one's a maximum and which one's a minimum, right? So good habits here. It's just for this problem, I knew the shape of this graph. I didn't really need to check, but if there is a case where you do end up with more than one critical number or a critical number that you're not really sure of, you want to, double check and check this derivative. I mean, this should take you like a minute or two to figure out. So it's not a loss of time. It's good habits and good practice. So we'll do a couple more examples